Welcome to Powered by Tesla.
All right, let's dive into a piece of technology that chances are you never really think about. But here's the thing, you use its product every single second of every day. We're talking about the alternator, the true unsung hero of our electrical world.
And no, that is not an exaggeration. I mean, think about it. The lights in your house, the computer you're on, the phone charging in the other room, nearly all of that energy started its journey inside one of these machines. They're also known as synchronous generators, and they are, hands down, the main source of the electricity we all use.
So, what exactly is it? Well, at its heart, an alternator is a master of transformation. It takes mechanical energy, like the spinning of a giant turbine pushed by steam or water, and through the magic of electromagnetic induction, it turns that into alternating current, or AC electricity. On a massive scale, there's simply nothing better at the job.
Now, you might be thinking, okay, it's a generator, I get it. But hold on. There is a really clever design choice deep inside the alternator that sets it completely apart from other generators, and it's this choice that makes it so perfect for powering the entire planet.
Okay, check this out. This is where the genius of the alternator really shines. Its design is basically the exact opposite of a DC generator. In an alternator, the part that actually creates the high-power electricity, called the armature winding, doesn't move. It's stationary. We call it the stator. Meanwhile, the magnetic field, which is a much lower power part of the system, is the bit that actually spins. And flipping the design like this, well, it changes absolutely everything.
So why is this flip so important? Well, think about it. If the part making all the high-voltage electricity is standing still, it's way easier to insulate it properly. It's not being ripped apart by massive centrifugal forces. You can connect the high-power output cables directly to it without any complicated sparking brushes. All the spinning part has to handle is a little bit of low-power DC current. The bottom line? The whole machine is simpler, way more robust, and can spin at incredibly high speeds, which means more power.
But here's the thing. Not all alternators are built to spin at the same speed. The design of the rotor, the spinning part, is totally customized for whatever is turning it, whether it's a water turbine or a steam engine. And this leads to two very, very different kinds of rotors. On one hand, for slower, powerful sources, like a giant water turbine in a dam, you use what's called a salient pole rotor. It's really wide and short, with these big magnetic poles that stick out. But for super high-speed steam turbines, you need something totally different. You need a non-salient or cylindrical rotor. It looks like a solid steel log, long and narrow, and it's built that way to handle the unbelievable stress of spinning thousands of times every minute. And the difference in speed is just staggering. Seriously, those salient pole rotors in a hydro plant might be turning at, a pretty relaxed pace. But the turbo alternators in a steam plant, they are absolutely screaming along at 1,500 or even 3,000 RPM. These are two completely different beasts, engineered for two very different jobs, but they have the exact same goal: create power at one perfectly stable frequency for the grid. So our alternator is spinning away, making voltage. Great. But that's only half the battle. The real interesting part, and frankly the really complex part, starts when you actually connect something to it, a load, and current begins to flow. Because that's when the machine's own output starts to fight back against itself. Right, so this is the key. Once that current starts flowing through the stationary armature windings, something new happens. That current creates its own magnetic field, and this new field immediately starts messing with the main magnetic field from the spinning rotor. This whole interaction has a name: armature reaction.
What this really means is that the load, your town, your factory, whatever, isn't just a passive sponge for electricity. By drawing current, the load actually creates a magnetic force that pushes back on the generator. And how it pushes back all depends on what kind of load you've connected. Okay, first up, a simple resistive load, like a big toaster or a heating element. In this case, the armature's magnetic field ends up kind of sideways to the main field. The result? It doesn't really make the main field weaker or stronger, it just distorts it. It kind of twists it out of shape.
But what about more common loads, like all the electric motors out there? These are inductive loads, and here the current lags behind the voltage. This puts the armature's magnetic field in direct opposition to the main field. It's like a magnetic head-on collision, and it has a powerful demagnetizing effect. It actually weakens the whole machine and makes the output voltage want to drop.
And then there's the third scenario, with a capacitive load. Here, the complete opposite happens. The current actually leads the voltage, and now the armature's magnetic field lines up with the main field. It helps it out. It strengthens the overall magnetism and makes the alternator's voltage want to rise. And this effect is actually super important for controlling voltage across the entire grid.
So we've got a pretty good handle on how one alternator works. But here's the thing. In the real world, no alternator is an island. They have to work as part of a massive, perfectly coordinated team.
Yeah, it's almost unheard of for one big generator to just power one thing by itself. Instead, just like our source material says, a huge number of them all running in parallel, all connected together through the national grid. The power station near you is working in perfect harmony with hundreds of others, hundreds of miles away.
And just to give you a sense of scale, a big interconnected grid might have a total capacity of over 40,000 megawatts. That is a staggering amount of power. But the largest single generator on that grid might only be around 500 megawatts. It's a system built entirely on teamwork.
So this brings up a huge question. How in the world do you do that? How do you take a massive spinning machine making hundreds of megawatts of power and safely plug it into a live electrical grid that's already humming along? You can't just throw a switch. The process is incredibly delicate, and it's called synchronization. To pull this off, 4 conditions have to be met perfectly. The voltage of the new alternator has to match the grid voltage. Duh, that makes sense. The frequencies have to be identical. Perfectly identical. And the 2 AC waveforms, the one from the alternator and the one on the grid, have to be perfectly in step, right at the same point in their cycle. And finally, the phase sequence has to be the same. If you get any one of these wrong, kaboom, catastrophic failure.
So why on earth go through all that trouble? Well, the payoff is huge. It gives us reliability. If one generator trips offline, the others instantly pick up the slack. It's super efficient because operators can bring generators online or take them offline to perfectly match the demand, keeping them all running at their sweet spot. It means you can do maintenance or add new power plants without ever shutting the whole system down.
And here's the coolest part. Once you get them synchronized, they want to stay that way. It's like they're all locked in a dance together. If one machine tries to speed up or slow down just a tiny bit, powerful magnetic forces are created between all the machines that just pull it right back in line. They are a self-correcting team.
When you really step back and look at it, the alternator is so much more than just a spinning hunk of metal. It's this powerful, elegant, and incredibly precise machine. It has to be both a brute force source of power and a delicate participant in this continent-wide dance of synchronization. It really is the stable, reliable backbone of everything we do.
And that kind of leaves us with one big question for the future. For more than a century, these huge spinning giants have given our grid the stability it needs to function. But now, as we add more and more renewable sources like solar and wind, which don't have that spinning mass, how is the role of the alternator going to change? What's the future for the machines that have silently powered our world for so long?
Like and share this video. And don't forget to subscribe to Powered by Tesla.